Hello and good morning, everyone, and welcome to this training session on concrete mix design and proportioning. And rather, I would say that it is a knowledge sharing session. And trust me, it doesn't matter whether you have any previous knowledge on concrete mix design or not. Still, if you have zero knowledge on this, still you will be able to design your concrete, the first concrete mix design by yourself with confidence. So that's my guarantee. But in return, I need something, and that is your complete attention. So this lecture will be around 1.5 hours to within 2 hours. So keep your mobile in silent mode. And with that, let's begin this session. Okay, first thing is that as a civil engineer, we most of the time deal with concrete, and now in the industry, in the construction industries, there are a variety of concrete is available, be it normal strength concrete or high strength concrete, then high performance concrete, and now uh, they are using ultra high performance concrete, then some self compacting concrete, then pavement quality concrete, then some fiber reinforced concrete, then polymer modified concrete, and the list goes on and on. So there are multiple type of concrete available in the market right now. And as a civil engineer, isn't it a good idea to know how they design those things? So it's a gradual process. In this session, we will focus on designing a normal strength concrete. So let's begin. Now, these are the objectives of this session. First, we will start by understanding what is nominal mix design and what are the advantages and limitations, and then we will know how to calculate the material quantities for 1 MQ of concrete for nominal mix concrete, and then difference between concrete mix design and concrete mix proportioning, and what are the steps involved, then the relationship between characteristic strength and target strength, and some key concepts that we must understand before we go on designing the mix, and how to find out the optimum dose of admixture, and then how to calculate the material quantities, and what is the importance of field trials. So these are some of the objectives of this session. So if you follow IS 456, then it specifies two different type of mix. One is design mix concrete and nominal mix concrete. So we will start by understanding what is a nominal mix. Now, before I proceed, I have a question: whether nominal mix means a volumetric mix or a weight mix. So as per IS 456, a nominal mix is a volumetric mix or a mix by its weight proportion. What is the answer? If you have answered that it is a volumetric mix, then my friend, you are absolutely wrong, because IS specifies nominal mix, different grades of nominal mix in the basis of weight. So let's first, I will show you that table later on. But first, let us understand what is nominal mix. What does nominal mix means? So it simply means you have some predefined values of different proportions that you can mix it at site, and directly you can use it. And IS specifically mentions that it is not a good idea to use nominal mixed concrete for any reinforced concrete structures. If you are doing any kind of PCC work, then you can use these mixes. And if in very unimportant structures or very minor works, you can use these nominal mixes. And the limitation or I would say the maximum grade of concrete that you can design with this nominal mix is M20 grade concrete. Now here is the table that I was talking about. This table specifies what is the quantities of different materials for 50 kg bag of cement. Now let's consider M20 grade concrete. So for each 50 kg bag of cement, you need 250 kg of fine aggregate plus coarse aggregate. And these fine aggregate and coarse aggregate is in the proportion of generally 1 is to 2, but it can vary from 1.1 is to 1.5 to 1 is to 2.5. And the maximum quantity of water you can use for M20 grade concrete is 30. So these the, the column 1 specifies different grades of concrete, and the column 2 gives you the quantities of material, quantities of aggregate, both fine and coarse, for 50 kg of cement. And the ratio of fine aggregate and coarse aggregate is in the proportion of 1 is to 2, which means if you are using 1 kg of fine aggregate, then you can use 2 kg of coarse aggregate. Then the last column says how what is the maximum amount of water you can use in that grade of concrete. So if you talk about 250 kg, then it means my one part is fine aggregate, my two part is coarse aggregate, and total it is 250 kg. So if I have to calculate the fine aggregate quantity for 50 kg bag of cement, then it would be 250 divided by 3. Let's calculate it what it comes. 1 minute. 250 divided by 3, 83.3. 83.3, let it be 83. And so the remaining amount is coarse aggregate. So 250 minus 83 is equal to 167. So for M20 grade concrete, the fine aggregate quantity is 83 kg and the coarse aggregate quantity is 167 kg. And the water, the maximum amount of water you can add is 30 kg. Now it has again said that this proportion, this 1 is to 2 proportion may vary from 1 is to 1.5 to 1 is to 2.5 depending upon the size of coarse aggregate. What it means, this whole table is for 20 size of aggregate. This whole table is for 20 sorry 20 size aggregate. If I change my maximum size of aggregate from 20 to 10 or 20 to 40, then my proportion will change accordingly. So instead, if I have to choose, if I am designing for same M20 grade concrete, but this time instead of using 20 aggregate, I am planning to use 10 aggregate. Then my proportion will become fine aggregate to coarse aggregate will become 1 is to 1.5. Then this quantity will change. So 250 divided by total 2.5. 250 divided by 2.5, 100 kg, and 100 kg will be my fine aggregate content, and 150 kg will be remaining 150 kg will be my coarse aggregate content. And if instead of 10, if it is 40 aggregate, then my fine aggregate to coarse aggregate content becomes 1 is to 2.5. So I have to divide 2.250 by 3.5. So 250 divided by 3.5, 71, approximately 71, and the remaining quantity will be 179, 179. So this will be my fine aggregate content, and this will be my coarse aggregate content. So depending upon the size of maximum size of aggregate that you are using, this ratio will change. Now coming to next slide, what will be the material requirement in kg for 1 mq of concrete? Now normally at site we use the unit of mq. While giving quantities or calculating quantities of concrete, we use the unit of mq. So it is important that somehow we need to convert this quantities which is specifically mentioned for 50 kg of a bag of cement. We need to convert that into quantities that will represent 1 mq of concrete. Let's find out how to do it. Now in our earlier calculations, we find out that for 1 minute, for M20, my cement is 50 kg. My final content was, considering 20 aggregate, it was 83. Coarse aggregate was 167. Water content is 30. In order to calculate the material requirement for 1 mq of concrete, we need to know what is the density of concrete. Now, as for Indian standard, the density of concrete is 2400 kg per mq. Now, what we need to do is we need to simply add all these material quantities. So, total material becomes 50 plus 83 plus 167 plus 30, 330. The total material quantity is 330. I need to divide it by divided 330. So 2400 divided by 330, which comes 7.27. Now what I will do next is I will multiply all these material quantities with 7.27. 7.27. So for cement content becomes 7.27, 363. Then my fine aggregate quantity becomes 83 into 7.27, 603. Then 167 into 7.27, 1214 kg. Then 30 into 7.27, 218. So this is the quantity of material required for 1 mq of concrete. So for 1 mq of concrete, I need a cement content of 363 kg, fine aggregate content of 603 kg, coarse aggregate content of 1214 kg, and water 218 kg a liter. Now let's do some back calculation and check whether all these materials, when we combine it together, is giving me 1 MQ or not. For that, we need to assume some specific gravity of all these materials. So let's assume specific gravity for cement, let it be 3.15. For coarse aggregate, let it be 2.75, or let it be 2.7 only. For fine aggregate, it is considered 2.65, and water 1. So now we will calculate from using these quantities. I will calculate the absolute volume of this material. So 365 divided by 3.15 divided by 1000, 0.11. The absolute volume becomes 0.11 for cement. Similarly, for coarse aggregate, 1214 divided by 2.7 divided by 1000, 0.449, consider 0.45, then for 603 divided by 2.65 divided by 1000, 0.22, 0.218. Now if I'll add all these volumes, let's see what I get. 0.11 plus 0.45 plus 0.22 plus 0.218, 0.998. So it is exactly coming out 1 MQ. So this is how you calculate quantities of material required for 1 MQ of concrete. Now let's move on further. What are the so these are the advantages and limitations of nominal mixed concrete. And the first advantage is that you don't need to wait for any person to come and design mix a concrete for M20 grade. If you are planning to do a PCC work and you need the material requirement for M20 grade, you can immediately, within just few minutes, you can calculate what will be the material quantities and you can start the work. No need to wait for anyone to come and do the mix design by doing some trials, and that way it saves you time. And uh, this way you can do the mix for only M20 grade concrete. But so there are some limitations also, and the limitation is that only up to M20 grade you can do this mix. And this is also, this proportion of this material quantities is valid only for considering that you are using some river sand. If your material changes, then this uh, quantities of material, particularly this water content, will not give you the required workability. And in some instances, if you need more workable, highly workable concrete, then this will not give you that. This material quantities will not give you that workability requirement. Also, use just for our previous calculation, we saw that the cement content needed for M20 grade concrete is above 350, 360. So this is not economical. So relying on M20, relying on nominal mix will not give you economical results. So these are some of the limitations of nominal mix, and that's why we need to know how the design mix is done. So the question is, what is the difference between concrete mix design and concrete mix proportioning? When we say mix design, we mean we need to establish what are the performance requirements of the concrete. So when we say mix design, we mean what are the performance requirements. The when we say performance requirements, it simply means how we want our concrete to behave when it is in fresh state and when it is in hardened state. So, what are our requirements in both of these two different states? So, most of the time during fresh state, our primary aim is to get a good level of workability so that we can handle it in our site. So what we do outside, we mix it, then we transport it, then with the available method of placement we place it, and then we compact it, then we finish it. So during all these different stages of concrete, concrete remains in fresh state, and we want our concrete to be in a way so that it is workable, so that it is workable with the available equipments or available methods we have. For example, if we are planning to do our concreting by a boom placer method, then we need to have required workability in terms of slump, that it be 150 or 120, or if you are doing some uh, concreting work using some chute, then that also needs some different level of workability. So accordingly, we need to decide what is our performance requirement in terms of fresh state, and during hardened state we primarily deal with strength, which is nothing but the characteristic compressive strength of concrete, or FCK. What is the strength requirement? We decide that thing also during the mixed design stage. So during fresh state we need to know its workability. We need to know also, along with that, we also need to know the durability requirements also in hardened strength. And when we say durability, we mean what should be the minimum quantity of cement content, what is the maximum allowable water cement ratio for that concrete, what type of structure you are doing, accordingly what type of material, most preferably what type of cement you need to use depending upon the environmental exposure conditions. Also, what is the dimension of the structure, because once you know the minimum dimension of the structures, accordingly you can decide what should be the maximum aggregate size that you can use. So there are other things. So the major thing is mixed design process. Once you know all the requirements, or once you finalize all your requirements in the mixed design stage, you the output will be used as an input for mixed proportioning process. Mixed proportioning, the next thing is mixed proportioning. From the mixed design stage, you finalize all these things. What will be your workability, what is your strength, what is your type of cement, what is your minimum cement content, what is your maximum water cement ratio, what type of what type of aggregate or other materials you need to use. So those things will be finalized during the mixed design stage. Once you finalize those things, the next step is to mixture proportioning, which simply means you have some previous experience, and based on that experience you know what will be the water cement ratio to start, or that is the one thing. And then mixed proportioning means finding out quantities of all the materials. That is nothing but some sort of calculations. Also, during mixed proportioning process, you do some tests on materials to see whether it is acceptable or not as per Indian standards. Then once your mixed proportioning is complete, then you do some trial mixes and you finalize your thing. And once that finalization, that final step achieves, then it gives you the batch proportions, because your mixed design is After the mix proportioning process, your mix, the quantities of material required will be finalized. But during at site, you need to adjust your materials depending upon the moisture conditions, and when you adjust that for moisture corrections, your batch proportions will be finalized, and these batch proportions will be directly fed into the RMC plant so as they will produce the concrete. So these are the different processes involved, and this is the major difference between designing and proportioning. When we say designing, we finalize all the things necessary for preparing a concrete, and when we say mixture proportioning, we simply means you just use your experience to find out what is the water cement ratio and all the calculations involved and all the tests you need to do to check whether your materials are falling in the as per the standards or not, meeting the standards requirement or not. So this difference between designing and proportioning. Moving on, this is the same thing. Design mix performance requirements and environmental conditions is a design mix. So definition of mixed design, you finalize your workability, you finalize your strength, then durability, then you consider economy, then you select suitable ingredients or materials, then you finalize the proportions. So this is the definition. It is a process of selecting suitable ingredients and determining their relative proportions with the objective of producing concrete of having certain minimum workability, strength and durability as economically as possible. This is the definition of mixed design. So now we will start our mixed design journey, and if you refer to IS 456, then it defines different, it it classifies concrete into different categories based on its strength. From M10 to M20, it classifies it as ordinary concrete. From M25 to M60, it classifies it as standard concrete. And from M65 to M100, it, it classifies it as high strength concrete. So in this training session, we'll mostly focusing on how to design a standard concrete, that is M25 to M60 grade concrete. So what are the data is required to do the mix design? As we discussed earlier, we need to know the workability and placement, how you are going to place your concrete. Accordingly, you have to decide your workability, that is some value. What is the transportation time? How long it will take the transit mixture from the production unit to reach at site. So method of placing, then site control, what is the degree of site control, what is if whether you are planning to use any admixture or not, whether you are using any mineral admixture or not, what is the minimum cement content, maximum water cement ratio. These are very important in terms of durability point of view, and some grade and type of cement, also some aggregate specification, what is the maximum nominal size, that will be based on the minimum dimension of your structure, and the opening size, the cover, that will tell you what is the maximum size of aggregate, and type of coarse aggregate, type of fine aggregate. So these are the uh, inputs that you require for designing a concrete mix, and these are the steps. So the first step is you calculate the target strength, and the next is you find out the air content, because no matter how well you compact your concrete, there is a chance that some amount of entrapped air will remain there. So you need to account for that in the design mix stage itself. So then you select the water content, then you select the admixture content, then you from water content and water cement ratio you finalize your cement content, then you calculate the total aggregate proportions, then you find out to coarse aggregate content, then fine aggregate content, and then you do some trial mixes. And once your lab trial mix is finalized, giving you adequate result, satisfying all the performance requirements, then you go for a field trial. This is the final stage, field trial. So these are the steps. Let's move on And this is the most important part of this training sessions, understanding some key concepts before we move on to designing our fast mix. So these are some of the concepts that we need to know. What is the relationship between water cement ratio and strength? What is the relationship between aggregate size and water content? Then water content and workability, and then coarse and fine aggregate combination. So we will discuss everything one by one. First, water cement ratio and strength. Suppose I have 1 liter of water and I used 500 gram of cement. I mixed 500 gram of cement in it. So my water cement ratio becomes, sorry, I have 500 liters of water and I added 1000 gram of cement in it. My water cement ratio becomes zero point 0.5. So this is my drone. As time passes, the cement will start to hydrate. Now just remember that the volume of hydration products of hydration will be more than the initial volume of cement grains. What I mean, if these are my cement grains, these red dot are cement grains, after when the hydration happens, this the some hydrated products will be formed, and those products will have higher volume than the initial volume. Now consider these white spaces are air, water, but as time passes, these water will evaporate and only hydrated products of cement will remain there, and those gaps, those air voids in between will remain there. And when air pockets or voids remain in a cement matrix, then it will weaken the structure and the strength will decrease. So if now suppose if I another here my I have increased my water content to 800, my cement content remains same. So I have again increased. So what happened as hydration happens? So some hydrated products will be formed, but the volume of air or volume of void will be higher because my cement content remain same and the hydration products will remain same, but as I have increased my water content, so the when the water content this water vapors sorry when these water content will remove from the system, then there will be only voids, and the more the voids, the lesser will be the strength of your concrete. So that's why water cement ratio and strength is inversely proportional to each other. If this is my strength and this is my water cement ratio, then the curve will look something like this. Now next try to understand aggregate size and water content. If my aggregate size will increase, then my if my aggregate size reduces, then my water content increases. Let my this is my water content, this is aggregate. So as aggregate size increases, my water demand decreases. Let me explain how this happens, why this happens. Suppose I have a cube. The cube have 6 faces. Now suppose the dimension of it has a dimension of 1 unit. So the surface area is 1 into 1, 1 square unit, and it has 6 faces. So the total surface, the total surface area is 6 units. Now suppose I cut this cube into half, both vertically and horizontally. I cut this cube into, so now a single cube has become 4 number of small size cubes. So this is, sorry, 4 number, no, 8 numbers of small size cubes. Now the size of each face becomes zero point 0.5 units. So my area becomes zero point 0.5 into 0.5, 0.25 units. It has 6 faces. So for a single small cube, the total area becomes 0.25 into 6, 1.5. But now I have total 8 numbers. So total area becomes, for all the 8 numbers including, 8 into 1.5, which becomes 12. Now though my volume remains same, but my surface area have doubled. My surface area has increased by 2 times. So what it means, that if I reduce my size of aggregate, then there will be increase in the surface area, and the more the surface area, the the more water will be required to coat around all the surface of that aggregate. So from this we can say that as the size of aggregate increases, your water demand reduces, or if your size of aggregate reduces, the water demand will be increased. So this is the concept number 2. Next, water content and workability. There is no need to explain here, because water is the only liquid material in this, all out of all the other materials. So if you need highly workable concrete, then you need to increase your water content. Then the final one is coarse aggregate and fine aggregate combination. Now a lot of experiments have been done, and they have concluded that let me draw a chart. Let this x-axis represents void, and this is the aggregate. Now if I only take any single size of aggregate, coarse aggregate I am talking about, graded coarse aggregate only, then if I consider 20 mm coarse aggregate, I have on no amount of fine aggregate, only graded aggregate, then I have a higher void content. But suppose I have replaced 20 percentage of coarse aggregate with 20 percentage of fine aggregate. Then there will be some reduction in void. As I gradually increase the fine aggregate percentage, then there will gradual reduction. But after a certain time, if you remove coarse aggregate and continue to add fine aggregate, then there will be no further decrease in void content. Rather, it will again start to go up. So the curve will look something like this. U curve. So at certain point, you will see that there will be no further decrease in void content. And above that, if you continue to replace your aggregate content by fine aggregate, then there will be again increase in void content. So this is the relationship between coarse and fine aggregate combination. Now let's move on. Different environmental exposure conditions. This is the most important thing. Whenever someone approach approach you to design a mix, then the very first thing that you need to understand is that what type of structure they are building, and most importantly, where the structure will be situated. Based on the location or area or the function of that structure, you have to decide what environmental exposure condition it belongs to, whether it is coming under mild environment or moderate or severe or very severe or extreme. Let's consider the example of in our case. In our case, we are doing pile foundations, and we are just few kilometers away from seashore. So if you consider this severe, then it said concrete exposed to coastal environment. So there are different conditions are given for different environmental conditions. You need to carefully go through these conditions, and accordingly you have to find out what is the best fit for that structure as per this environmental conditions. And you have to finalize the environmental conditions, because based on these environmental conditions you have to decide your maximum water cement ratio, and you have to decide based on this environmental condition, you have to decide your minimum amount of cement content. So let's move on. Next thing is, what is the characteristic strength versus what is the relationship between characteristic strength versus target strength. I will uh, i will keep this thing, I will take up this thing later on at the end of this presentation if time allows. For the time being, I am skipping this part of this presentation. I will tell you that the first step for designing a concrete mix is to calculate the target mean strength, and this is the formula that we use for calculating target mean strength. Here, this FCK is nothing but the characteristic compressive strength. For example, if we are designing for M35 grade, then this is 35, and this is 1.65 is a constant, and this is the standard deviation. I will skip these things, but later on I will catch up. Okay, let's start by doing an example. So these are these are the given data. We need to design for M35 grade concrete, and our workability requirement is 150 mm, and the exposure condition is very severe. And we will use OPC 43 grade. Our maximum size of aggregate is 20 mm, and we have tested the sand, and it is coming under zone 1, and the shape of aggregate is angular, and these are some of the specific gravitative values of different materials. So the step one is to calculate the target mean strength of concrete. So FCK, we know it is a constant. The only thing we need to find out is this standard deviation. IS 456 gives the values of standard deviation for different grades of concrete. So as we are designing for M35 grade of concrete, the standard deviation is 5. So we put that value in this equation and it comes around 43.4 Newton per mm square. For the sake of to be on safe side, let's assume it to be 45 Newton per mm square. Now move on. Now we know the target mean strength. The next important step is to find out what is the required water cement ratio to achieve that target mean strength. Now to do that, if you have already have some experience with concrete, with that type of cement, then you can from your experience can assume some values of water cement ratio. But if you don't have any previous knowledge, then in that case you can refer to this chart. This is a chart given in IS 10262. Let me write it down. IS 10262 2019. This is the code of this is the code we refer for concrete mix proportioning. This code gives you this chart. It has three curves: curve 1, 2, 3. Curve 1 is for OPC 33, then for 43, then curve 3 for 53. Also, if you are not using any OPC grade cement, you are using any PPC or PSC cement, then standard suggests that you refer the curve 2. Now in our case, our target strength is 45. So this is the 20 days compressive strength. 45 is here. So we need to draw a horizontal line until it touches this curve 2, and then we need to draw a vertical line until it reaches this water cement ratio. So from here we can see the water cement ratio is 0.37. So this is the starting point. Now we know the water cement ratio. Now we need to refer to IS 456 to see whether this water cement ratio is permissible depending upon the environmental exposure condition. So in our case we are designing a concrete for very severe condition. Let's see what standard specifies for very severe condition. So here is the table that shows you for plain cement, for plain cement and for RCC concrete, what is the different values of minimum cement content and maximum free water cement ratio and minimum grade of concrete for different exposure conditions. So here for very severe condition and for RCC, it says that you need to have a minimum cement content of 340, maximum water cement ratio of 0.45, and minimum grade of concrete that you need to use is N35. So accordingly we have to proceed further. So our what we have calculated that our water cement ratio from that curve is 0.37 and it is under 0.45, so it's okay. Now let's move on, and here the second step is to estimate the air content based on different size of maximum aggregate, different sizes of aggregate. Some predefined values of entrapped air content is given. You can directly consider that. As we are using 20 mm size aggregate, I specifies a 1% volume of entrapped air. Then next step is to decide the water content. Here for different size of maximum size aggregate, different quantities of water per m cube concrete has given. For 20 it is 186. Here for 20 aggregate, the value of water content is 186. But it is, some conditions are there to use this 186 kg of water content, and the conditions are: if you require a slump value of only 50 and your shape of aggregate is angular, then only that case you can use this value of 186. You can use this value only if your slump requirement is 50 and your aggregate is angular in shape. So but in our case we need a slump of 150 The second requirement is valid, we have angular aggregate, but here instead of 50 we need a slump of 150. So how to do the adjustment for that? IS specifies that for each 25 increase of slump you need to add 3% extra water. What it means, for 20 the required water content is 186, but this is valid when you require only 50 slump. But what standard says, if your required slump is above this value, then for each additional 25 of slump you need to increase this water content by 3%. So in our case we have some additional slump value of 100. We need 150, but the addition is only 100 So 100 means 4 times this 25 So we need to increase this water content by 4 times of 3%, which means 12%. So final water content will become 186 plus 12% of 186. So total water content will become 208 liters. Next, so here is an extra thing that I have shown, because we have angular aggregate there, so we uh, have to do no adjustment for the aggregate. But still, in case you have aggregate shape other than angular, then you also need to do some adjustment. This code says that if your aggregate is subangular, then you can reduce that water content by 10 kg. Suppose from for 20 the water content was 186, and it is valid when your aggregate is angular in shape. But if your aggregate is subangular, then you can directly reduce 10 kg. So your final water content will be 176. If you have gravel with crust particle, then you can subtract 15 kg, and your final water content will be 171. And if you have rounded gravel, then you can reduce it by 20 kg, 166. So these are the some of the corrections you can do if you have a different shape of aggregate. Now moving on, we already know our water content, which is 208 kg. We know our water cement ratio, which is 0.37. Now from that two values we can calculate what is the requirement of what is the quantity of cement. Simply we divide to 208 divided by 0.37, it is 562 kg, and we need to compare this 562 kg of cement with the requirement of minimum cement content. If you refer back to that standard, then it says that for very severe condition, the minimum cement content is required is 340 kg. So in our case, it is 350, 350, 562 kg. So it is absolutely okay. No need to worry about that. And check some other minimum requirements. In some cases, standard says that if you have if you are doing some underwater concreting, then in that case your minimum cement content requirement is 380 kgs, so you need to check that also. So in any case, it is satisfying the minimum cement requirement criteria. But what about the maximum cement content criteria? Because IS specifically mentions that if you are using OPC cement exclusive of any pozzolanas, any fly ash or slag, exclusive of any pozzolanas, if you are using only OPC, then that content should not be more than 450 kg. If you are using above 450 kg, then some designers consent you have to take. So let's keep this, reduce this cement content to 5 to be under 450 kg. Then how to do it? Simply by using admixtures. Because admixtures, I'm talking about super plasticizers, because when you use plasticizers or super plasticizers, then they reduce the water content without compromising your workability, and thereby they help you reduce the cement content accordingly. But the question is, how can we know what is the optimum dose of admixture we need to use in our case? There is a simple test called Mars cone test. Using this test, you can do some simple test and find out what is the optimum dose of admixture for that to be used for that type of cement. In this test, what you do, you prepare a cement slurry of nearly 1 liter of volume, and you add a few dose of admixture in it. Let it be zero point 0.2, zero point 0.3, or as per manufacturer's recommendations. And then you uh, you open this gate and you allow this cement slurry to flow into this cylinder, and you start the stopwatch. When you remove this gate, you start the stopwatch and you record how long does it take for all this 1 liter of slurry to fill this glass measuring cylinder, and you record the time. And when you gradually increase the dose of admixture, you finally reach a point when there will be no change in this of time when you further add the dose of admixture. And from that you draw a curve, and from this curve you finalize what is the optimum dose. You see here, after this there will be no further decrease in the Mars cone time. So you can say this is the optimum dose. If you unnecessarily add more admixture, then it is not helping you. It is only you are only consuming without any result. So accordingly you have to decide the optimum dose. And once you find out the optimum dose, the next step is to do the correction accordingly. So from this experiment, you found that you can use 1% by mass of cement, and which will reduce the water content by 25%. So now my final water content becomes 156 liter. Now next you have to again calculate what will be the cement content for this amount of water content. And how to do it? You already know the water cement ratio. So 156 divided by 0.37, now it is coming 421 kg. Again you compare it with your minimum cement content requirement. So your minimum is 340 and it is above that, so it is okay. And your maximum cement content requirement, the maximum allowable cement content for OPC is 450, it is below that. So finally you have reached your cement content. Now moving on, now you need to decide your coarse aggregate proportion. As we have discussed in our key concept part, what from the total aggregate portion, what will be your coarse aggregate fraction, volume of coarse aggregate. So for different maximum size of aggregate and different zones of fine aggregate, there are different volume of coarse aggregate. So in our case, our aggregate size is maximum size is 20, and our zone is, from the test we know that it is falling with the fine aggregate is falling under zone 1. So our the so 60% is the volume of coarse aggregate from the total aggregate. This is 60%. Next, estimation of coarse aggregate. Now this point 0.6 is valid only if the water cement ratio is point point 0.5, but in our case the water cement ratio is 0.37. Again we need to do some corrections for this also. So what that correction is, standard says for every increase or every decrease in 0.01, there will be a, it says the proportion of volume of coarse aggregate to that of total aggregate is increased at the rate of 0.01 for every decrease in water cement ratio by 0.05, and vice versa. So in our case the difference in water cement ratio is 0.13. So the corrections will be, applying the formula, it will be 0.626. So what does it mean? That if my total aggregate content is 1, then 62.6% will be my coarse coarse aggregate, and remaining will be my fine aggregate. So you subtract that value from 1, and this will give you the fine aggregate volume. Now we know what is the, now let's calculate what are the requirement, what are the different proportions by volume. So our total volume was 1 mq, and from that we need to subtract the volume of air, entrapped air from that. So it was 1%. So the my fine, so this is the 0.01 mq. Then volume of cement, you just divide it by its specific gravity, and it will give you the volume of cement, absolute volume of cement. Then you get the volume of water, then volume of admixture. You know, the as we find out that admixture quantity is 1% by mass of cement. Our cement was 421 kg, so 1% of 421 is 4.21. So that's why you know the specific gravity of admixture and you find out the volume. So and the volume of total aggregate means 1 minus, you add all the things and you subtract it from 1, and that will give you, this is the volume of total aggregate. Total aggregate. Next, so out of this total aggregate, this is the total aggregate volume, and we know that 62.6% is coarse aggregate and 37.4 is fine aggregate. So accordingly you put those values into the formula and you get the weight of each material. So here is a pie chart that shows you different shows you in percentage different volume of different materials. So 44% is by volume of cement, then fine aggregate, then water, then coarse aggregate. In the same manner, it is different percentage by weight of different material. These are two same pie charts. The left side is these percentages are on the basis of volume, and these percentages are on the basis of volume. Now I have a question. Now you see here water content percentage by volume is showing 16%, but here in terms of weight it is giving you only, it is showing you only 7%. Why is so much of variation in this? This is because water is the lightest material among all the materials we have in concrete. Has a specific gravity of only 1, though it is occupying a significant volume in terms of volume, but in terms of weight it has less weight. That is the reason. Now we have done. Then next thing is finding out the moisture correction. Now until now we have calculated all the materials which are in SSD condition, but in practical it is impossible to get all your materials in SSD conditions. Either you will find it the water content is less than the SSD condition or more than the SSD conditions. Now let's know how to do the adjustments for that. Now let's first consider the dry condition, when the materials are in dry conditions. But before you do it, you need to know what are the absorption, the values of water absorption for each material. Here we are talking about only fine aggregate and coarse aggregate. So in dry case, all your materials are in dry state. What means by SSD? Because SSD simply means your materials have absorbed enough water, but the surface is not wet, only they have absorbed enough water. So you see, when you have, if you don't do any adjustment, then these dry aggregates will absorb water from these quantities. From this quantity they will absorb some water, thereby it will affect the workability of your concrete. Your concrete will become very stiff. Therefore you need to add some additional water when your aggregates are in dry conditions. And how do you find out those additional water content? Simply, this is your fine aggregate content. So you find out what is the 1% of 691. 691 1%. What that value is, let's calculate it. 691, and similar way 0.5%. So my total water content becomes 6.91 plus 5.89, 12.8. 12.8. So in this 156, I need to add this 12.8, let it be 13. So my final water content becomes 169. So here 169, and also we need to subtract this amount from these values, so that when they absorb water, the value will become this. So if I reduce the quantities of my coarse aggregate after absorbing enough water to make them SSD, the final weight of aggregate will become 691 and 1178 respectively. So this is the way to calculate do the moisture correction for when the aggregates are in dry state. Similarly, I gave you the task of finding out what will be the correction of water, what will be the moisture correction during the wet case during the rainy season. Now, now the next thing is done your you have get your you have your all the material quantities, and you do the fast trial mix. I'm talking about lab trial mix. You did your lab trial and you observe some kind of segregation or bleeding. In that case, you need to adjust the water content or admixture dose, or in some cases you need to change the percentage of coarse aggregate and fine aggregate to just adjust in a way so that your segregation and bleeding should not happen. And once you do that, and in your adjustment you're of you get the uh, you get your performance requirements, then you do further two more trials by increasing and decreasing the water cement ratio by zero point 0.01. Oh, sorry, zero point 0.1. What I mean, so in the your first trial, if it is giving you enough performance requirement, suppose it is giving you the retention time that you need, it is giving you the slump requirement, it is not segregating, it is not bleeding, then the first trial, then it's okay. Again, you have to do further two trials by changing the water cement ratio by zero point 0.1. Suppose in our case, if it is 0.37, then we need to do additional two trials for 0.36 and for 0.38. But if your first trial is not giving you the best results that you are expecting, then you need to change the admixture dose, or you need to change the coarse aggregate to fine aggregate proportion, and accordingly you have to do a second trial. So it is expected that during second trial you will get all of your results quite well, and then you need to do the changes in water cement ratio and do the calculations again accordingly these changed water cement ratio, and you have to find out all the quantities, and again you do the trial mix, and uh, so you cast some cubes, because this is very important step. Once you do this, you can generate an correlations between water cement ratio and strength. So here trial mix 1 2 3 with some changed water cement ratio. You started trial mix number 1, then you decrease it a bit, and you increase it by zero point 0.1, and accordingly you develop a correlation between your strength, concrete strength, and your water cement ratio. This will be very helpful in case in a situation you found that your concrete is failing. In that case, you can directly refer to this chart and take some immediate steps to carry on the work without stopping the work. So this is very important. Now your lab trial part is over. Then comes the field trial. In case of why field trial is important, because in the lab you are doing everything in a controlled environment, but in field you have no such control over your environment. The second thing is that when you are at site, you are mixing concrete in huge you are mixing concrete in huge quantities. In the lab you are just making a small batch, just zero point 0.2 zero point 0.02 mq or like that. But in batching plant you are mixing zero point 0.5 mq of concrete.
so the material quantity increases. So accordingly, there may be some differences in hydration, or there may be something may happen. Then another thing is that the sequence of addition of materials. So the way you have added all the materials in lab trial may not be same when you use a batching plant. So there are sequence of, because sequence of addition of material also have some effect on your fresh concrete. So that's why there are a lot of variation that may happen outside. Therefore, you need to consider a field trial. This is very important, but mostly neglected, but very, very important. So once you do the field trial and you check the performance of concrete during its fresh state and you find it adequate, then you cast some cues and you check its performance after 28 days and everything is fine, then your concrete mix design is finalized. And the final, this is the end of this training session. And the final thing that I want to say with that, this is what I have shared with you, just the beginning of your journey to become a concrete to become a concrete technologist, or to start your journey as a concrete mix designer. So you need to have a lot of experience. You need to go to a site to see what are the difficulties you actually find. Whenever you are doing any mix design, go to that lab to see the things by yourself. And when you do that, you gain the knowledge by observations. And once you have some enough understanding of the concept, or enough understanding by seeing the things happening in front of you, you gain confidence to do it a better way. So hopefully uh, you have gained some insights from this training session. Thank you. Any questions? Please go on.